Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 7. System of Nonlinear Equations. Newton's Method. Nonlinear systems of equations are frequently encountered in many branches of science and engineering because most physical systems occurring in nature are inherently nonlinear. Nonlinear systems of equations can be very complicated and difficult to solve if the system variables are highly interdependent. The numerical solution of systems of nonlinear equations is one of the major challenges facing a numerical analyst today. Bracketing methods are very difficult to implement for such cases. The best option, for being very simple and effective, is Newton's method, an extension of the Newton-Raphson method to multivariable functions. Now, we extend Newton's method to n simultaneous nonlinear equations with n unknowns, where x is the vector of unknown variables. Fx is the vector of nonlinear functions from f1 to fn. To develop the algorithm for the Newton's method, we make use of the generalized Taylor series expansion of the function f about xp. Higher-order terms can be neglected if the current estimate is sufficiently close to the prior estimate. Where delta p is the displacement vector, x, p plus 1, and xp are the vectors containing the current and prior estimates. The Jacobian is constructed by taking the partial derivatives of the functions f1 to fn with respect to every independent variable. The Jacobian is evaluated at prior estimates. If x, p plus 1, is sufficiently close to the true solution, the vector fx, p plus 1, will approach 0. So setting the vector of current estimates to 0, we find, which should be solved using a direct method at every iteration step, because the linear system may be ill-conditioned. The Jacobian matrix for a small number of nonlinear equations can be inverted using a symbolic processor to obtain the solution as follows. The current estimates are then obtained from x, p plus 1, equals xp plus delta p. A convergence test may be prescribed in terms of the norms of the displacement vector. The advantages of Newton's method are: Newton's method is easy to understand and implement. It can be applied to solve a variety of problems. If a solution exists, it converges at a quadratic convergence rate with a good set of initial guesses, i.e., the error is squared or the number of accurate digits doubles at each iteration step. The disadvantages of Newton's method are: the method may fail to converge, or convergence difficulties may be observed if the system is very sensitive to initial values. The Jacobian should be constructed, preferably analytically, which can be tedious for large or complex systems. The Jacobian and its inverse have to be calculated at each iteration step, which can be quite time-consuming depending on the system size. The resulting linear systems are generally not suitable to be solved by iterative methods. For ill-conditioned systems, Jacobians with very large condition numbers, a suitable corrective algorithm should also be employed. Consider the following system of nonlinear equation. Apply Newton's method to obtain a set of approximate solutions. Use 1 as the initial guess and 6 times 10 to the minus 5 as the convergence criterion for the Euclidean norm of the displacement vector. The iteration equation has the matrix equation form, where delta is the displacement vector. The matrix J is the Jacobian matrix, which is constructed by taking the partial derivative of f1 with respect to x and y. and partial derivatives of f2 with respect to x and y. Starting with the initial guess, we calculate f1 and f2 as follows. Now, we evaluate the Jacobian for x0 equals 1 and y0 equals 1. Solving the resulting 2 by 2 system for the displacement vector yields 1.8 and minus 0.4. Then, we update the estimates by adding the displacement vector to the initial guess vector, which yields x1 equals 2.8 and y1 equals 0.6. We repeat the process for x1 and y1. Function f1 and f2 are evaluated as follows. Next, we construct the Jacobian matrix and solve the system of 2 by 2 equations for the displacement vector delta 1, which results in delta 1 equals minus 0.622696 and delta 2 equals 0.350828. The second estimate is obtained by adding the displacement and first estimate vectors, which gives x2 equals 2.17730 and y2 equals 0.950828. Repeating this procedure, the converged estimate for the system of nonlinear equations is obtained as x equals 2.011, 550, and 1.11, 2790. The Euclidean norm of the displacement vector satisfies the convergence condition. That is all for now. See you next time with another topic. Bye.